A chemical element is a pure chemical substance consisting of a single type of atom distinguished by its atomic number, which is the number of protons in its atomic nucleus. Elements are divided into metals, metalloids, and nonmetals. The lightest chemical elements, including hydrogen, helium and smaller amounts of lithium, beryllium and boron, are thought to have been produced by various cosmic processes during the Big Bang and cosmic ray spallation. Production of heavier elements, from carbon to the very heaviest elements, preceded by stellar nucleosynthesis, and these were made available for later solar system and planetary formation by planetary nebulae and supernovae, which blast these elements into space. The high abundance of oxygen, silicon, and iron on Earth reflects their common production in such stars. While most elements are generally stable, a small amount of natural transformation of one element to another also occurs in the decay of radioactive elements as well as other natural nuclear processes. The history of the discovery and use of the elements began with primitive human societies that found native elements like copper and gold and extracted iron and a few other metals from their ores. Alchemists and chemists subsequently identified many more, with nearly all of the naturally occurring elements becoming known by 1900. The properties of the chemical elements are often summarized using the periodic table, which organizes the elements by increasing atomic number into rows in which the columns share recurring physical and chemical properties. Save for unstable radioactive elements with short half-lives, all of the elements are available industrially, most of them in high degrees of purity. Hydrogen and helium are by far the most abundant elements in the universe. However, iron is the most abundant element making up the Earth, and oxygen is the most common element in Earth's crust. Although all known chemical matter is composed of these elements, chemical matter itself is hypothesized to constitute only about 15% of the matter in the universe. The remainder is believed to be dark matter, a range of substances whose composition is largely unknown and not composed of chemical elements, since it lacks protons, neutrons or electrons. Dark matter may also include normal baryonic matter and neutrinos. When two or more distinct elements are chemically combined, with the atoms held together by chemical bonds, the result is termed a chemical compound. 2/3 of the chemical elements occur naturally on Earth only as compounds, and in the remaining third, often the compound forms of the element are most common. Chemical compounds may be composed of elements combined in exact whole number ratios of atoms, as in water, table salt, and minerals such as quartz, calcite, and some ores. However, chemical bonding of many types of elements results in crystalline solids and metallic alloys for which exact chemical formulas do not exist. Relatively pure samples of isolated elements are uncommon in nature. While 98 naturally occurring elements have been identified in mineral samples from Earth's crust, only a small minority of elements are found as recognizable, relatively pure minerals. Among the more common of such native elements are copper, silver, gold, carbon, sulfur, and mercury. All but a few of the most inert elements, such as noble gases and noble metals, are usually found on Earth in chemically combined form, as chemical compounds. While about 32 of the chemical elements occur on Earth in native uncombined forms, most of these occur as mixtures. For example, atmospheric air is primarily a mixture of nitrogen, oxygen, and argon, and native solid elements occur in alloys, such as that of iron and nickel. As of November 2011, 118 elements have been identified, the latest being unseptium in 2010. Of the 118 known elements, only the first 98 are known to occur naturally on Earth. 80 of them are stable, while the others are radioactive, decaying into lighter elements over various timescales from fractions of a second to billions of years. The 18 radioactive elements that occur naturally are either very long-lived isotopes or else radioactive decay daughters or nuclear reaction products formed from these elements combining with naturally occurring neutrons. Those elements that do not occur naturally on Earth have been produced artificially as the synthetic products of nuclear reactions. Description: the lightest of the chemical elements are hydrogen and helium, both created by Big Bang nucleosynthesis during the first 20 minutes of the universe in a ratio of around 3:1 by mass. Almost all other elements found in nature were made by various natural methods of nucleosynthesis. On Earth, small amounts of new atoms are naturally produced in nucleogenic reactions, or in cosmogenic processes, such as cosmic ray spallation. New atoms are also naturally produced on Earth as radiogenic daughter isotopes of ongoing radioactive decay processes such as alpha decay, beta decay, spontaneous fission, cluster decay, and other rarer modes of decay. Of the 98 naturally occurring elements, those with atomic numbers 1 through 40 are all considered stable. At least one isotope of each element with atomic numbers 41 through 82 are apparently stable but theoretically unstable and thus possibly mildly radioactive. The half-lives of elements 41 through 82 are so long, however, that their radioactive decay remains undetected by experiment. These theoretical radionuclides have half-lives at least 100 million times longer than the estimated age of the universe. Elements with atomic numbers 83 through 98 are unstable to the point that their radioactive decay can be detected. Some of these elements, notably thorium, uranium and plutonium, have one or more isotopes with half-lives long enough to survive as remnants of the explosive stellar nucleosynthesis that produced the heavy elements before the formation of our solar system. For example, at over 1.9 1019 years, over a billion times longer than the current estimated age of the universe, bismuth 209 has the longest known alpha decay half-life of any naturally occurring element. The very heaviest elements undergo radioactive decay with half-lives so short that they do not occur in nature and must be synthesized. As of 2010, there are 118 known elements. Of these 118 elements, 98 occur naturally on Earth. 10 of these occur in extreme trace quantities: technetium, atomic number 43; promethium, number 61; astatine, number 85; francium, number 87; neptunium, number 93; plutonium, number 94; americium, number 95; curium, number 96; berkelium, number 97; and californium, number 98. These 98 elements have been detected in the universe at large, in the spectra of stars and also supernovae, where short-lived radioactive elements are newly being made. The first 98 elements have been detected directly on Earth as primordial nuclides present from the formation of the Solar System, or as naturally occurring fission or transmutation products of uranium and thorium. The remaining 20 heavier elements, not found today either on Earth or in astronomical spectra, have been produced artificially. These are all radioactive, with very short half-lives. If any atoms of these elements were present at the formation of Earth, they are extremely likely, to the point of certainty, to have already decayed, and if present in novae, have been in quantities too small to have been noted. Technetium was the first purportedly non-naturally occurring element synthesized, in 1937, although trace amounts of technetium have since been found in nature. This pattern of artificial production and later natural discovery has been repeated with several other radioactive naturally occurring rare elements. Lists of the elements are available by name, by symbol, by atomic number, by density, by melting point, and by boiling point, as well as ionization energies of the elements. The nuclides of stable and radioactive elements are also available as a list of nuclides, sorted by length of half-life for those that are unstable. One of the most convenient, and certainly the most traditional presentation of the elements, is in the form of the periodic table, which groups together elements with similar chemical properties. Atomic number. The atomic number of an element is equal to the number of protons in each atom, and defines the element. For example, all carbon atoms contain 6 protons in their atomic nucleus. So the atomic number of carbon is 6. Carbon atoms may have different numbers of neutrons. Atoms of the same element having different numbers of neutrons are known as isotopes of the element. The number of protons in the atomic nucleus also determines its electric charge, which in turn determines the number of electrons of the atom in its non-ionized state. The electrons are placed into atomic orbitals that determine the atom's various chemical properties. The number of neutrons in a nucleus usually has very little effect on an element's chemical properties. Thus, all carbon isotopes have nearly identical chemical properties because they all have 6 protons and 6 electrons, even though carbon atoms may, for example, have 6 or 8 neutrons. That is why the atomic number, rather than mass number or atomic weight, is considered the identifying characteristic of a chemical element. The symbol for atomic number is Z, isotopes. Isotopes are atoms of the same element, but having different numbers of neutrons. Most naturally occurring elements have more than one stable isotope. Thus, for example, there are 3 main isotopes of carbon. All carbon atoms have 6 protons in the nucleus, but they can have either 6, 7, or 8 neutrons. Since the mass numbers of these are 12, 13 and 14 respectively, the 3 isotopes of carbon are known as carbon-12, carbon-13, and carbon-14, often abbreviated to 12C, 13C, and 14C. Carbon in everyday life and in chemistry is a mixture of 12C, 13C, and 14C atoms. Except in the case of the isotopes of hydrogen, the isotopes of a given element are chemically nearly indistinguishable. All of the elements have some isotopes that are radioactive, although not all of these radioisotopes occur naturally. The radioisotopes typically decay into other elements upon radiating an alpha or beta particle. If an element has isotopes that are not radioactive, these are termed stable isotopes. All of the known stable isotopes occur naturally. The many radioisotopes that are not found in nature have been characterized after being artificially made. Certain elements have no stable isotopes and are composed only of radioactive isotopes. Specifically, the elements without any stable isotopes are technetium, promethium, and all observed elements with atomic numbers greater than 82. Of the 80 elements with at least one stable isotope, 26 have only one single stable isotope. The mean number of stable isotopes for the 80 stable elements is 3.1 stable isotopes per element. The largest number of stable isotopes that occur for a single element is 10. Isotopic mass and atomic mass. The mass number of an element, A, is the number of nucleons in the atomic nucleus. Different isotopes of a given element are distinguished by their mass numbers, which are conventionally written as a superscript on the left-hand side of the atomic symbol. The mass number is always a simple whole number and has units of nucleons. An example of a referral to a mass number is magnesium-24, which is an atom with 24 nucleons. Whereas the mass number simply counts the total number of neutrons and protons and is thus a natural number, the atomic mass of a single atom is a real number for the mass of a particular isotope of the element, the unit being U. In general, when expressed in U, it differs in value slightly from the mass number for a given nuclide, since the mass of the protons and neutrons is not exactly 1 U. Since the electrons contribute a lesser share to the atomic mass as neutron number exceeds proton number, and because of the nuclear binding energy. For example, the atomic mass of chlorine 35 to 5 significant digits is 34.969 U and that of chlorine 37 is 36.966 U. However, the atomic mass in U of each isotope is quite close to its simple mass number. The only isotope whose atomic mass is exactly a natural number is 12C, which by definition has a mass of exactly 12, because U is defined as 1/12 of the mass of a free neutral carbon-12 atom in the ground state. The relative atomic mass of an element is the average of the atomic masses of all the chemical elements isotopes as found in a particular environment, weighted by isotopic abundance, relative to the atomic mass unit. This number may be a fraction that is not close to a whole number, due to the averaging process. For example, the relative atomic mass of chlorine is 35.453 U, which differs greatly from a whole number due to being made of an average of 76% chlorine 35 and 24% chlorine 37. Whenever a relative atomic mass value differs by more than 1% from a whole number, it is due to this averaging effect resulting from significant amounts of more than one isotope being naturally present in the sample of the element in question. Chemically pure and isotopically pure. Chemists and nucleoscientists have different definitions of a pure element. In chemistry, a pure element means a substance whose atoms all have the same atomic number, or number of protons. Nucleoscientists, however, define a pure element as one that consists of only one stable isotope. For example, a copper wire is 99.99% chemically pure if 99.99% of its atoms are copper, with 29 protons each. However, it is not isotopically pure since ordinary copper consists of two isotopes, 69% 63 Cu and 31% 65 Cu, with different numbers of neutrons. Allotropes. Atoms of chemically pure elements may bond to each other chemically in more than one way, allowing the pure element to exist in multiple structures, known as allotropes, which differ in their properties. For example, carbon can be found as diamond, which has a tetrahedral structure around each carbon atom. Graphite, which has layers of carbon atoms with a hexagonal structure stacked on top of each other. Graphene, which is a single layer of graphite that is very strong. Fullerenes, which have nearly spherical shapes. And carbon nanotubes, which are tubes with a hexagonal structure. The ability of an element to exist in one of many structural forms is known as allotropy. The standard state, also known as reference state, of an element is defined as its thermodynamically most stable state at 1 bar at a given temperature. In thermochemistry, an element is defined to have an enthalpy of formation of 0 in its standard state. For example, the reference state for carbon is graphite, because the structure of graphite is more stable than that of the other allotropes. Properties. Several kinds of descriptive categorizations can be applied broadly to the elements, including consideration of their general physical and chemical properties, their states of matter under familiar conditions, their melting and boiling points, their densities, their crystal structures as solids, and their origins. General properties. Several terms are commonly used to characterize the general physical and chemical properties of the chemical elements. A first distinction is between metals, which readily conduct electricity, known metals, which do not, and a small group having intermediate properties and often behaving as semiconductors. A more refined classification is often shown in colored presentations of the periodic table. This system restricts the terms metal and known metal to only certain of the more broadly defined metals and known metals, adding additional terms for certain sets of the more broadly viewed metals and known metals. The version of this classification used in the periodic tables presented here includes actinides, alkali metals, alkaline earth metals, halogens, lanthanides, other metals. Metalloids, noble gases, polyatomic known metals, diatomic known metals, and transition metals. In this system, the alkali metals, alkaline earth metals, and transition metals, as well as the lanthanides and the actinides, are special groups of the metals viewed in a broader sense. Similarly, the polyatomic known metals, diatomic known metals and the noble gases are known metals viewed in the broader sense. In some presentations, the halogens are not distinguished, with astatine identified as a metalloid and the others identified as known metals. States of matter. Another commonly used basic distinction among the elements is their state of matter, whether solid, liquid, or gas, at a selected standard temperature and pressure. Most of the elements are solids at conventional temperatures and atmospheric pressure, while several are gases. Only bromine and mercury are liquids at 0 degrees Celsius and normal atmospheric pressure. Cesium and gallium are solids at the temperature, but melt at 28.4 degrees Celsius and 29.8 degrees Celsius, respectively. Melting and boiling points, typically expressed in degrees Celsius at a pressure of 1 atmosphere, are commonly used in characterizing the various elements. While known for most elements, either or both of these measurements is still undetermined for some of the radioactive elements available in only tiny quantities. Since helium remains a liquid even at absolute zero at atmospheric pressure, it has only a boiling point, and not a melting point, in conventional presentations. Densities. The density at a selected standard temperature and pressure is frequently used in characterizing the elements. Density is often expressed in grams per cubic centimeter, Since several elements are gases at commonly encountered temperatures, their densities are usually stated for their gaseous forms. When liquefied or solidified, the gaseous elements have densities similar to those of the other elements. When an element has allotropes with different densities, one representative allotrope is typically selected in summary presentations, while densities for each allotrope can be stated where more detail is provided. For example, the three familiar allotropes of carbon have densities of 1.8 to 2.1, 2.267 and 3.515 grams per centimeter 3, respectively. Crystal structures. The elements studied to date as solid samples have 8 kinds of crystal structures: cubic, body-centered cubic, face-centered cubic, hexagonal, monoclinic, orthorhombic, rhombohedral, and tetragonal. For some of the synthetically produced transuranic elements, available samples have been too small to determine crystal structures. Occurrence and origin on Earth. Chemical elements may also be categorized by their origin on Earth, with the first 98 considered naturally occurring, while those with atomic numbers beyond 98 have only been produced artificially as the synthetic products of man-made nuclear reactions. Of the 98 naturally occurring elements, 84 are considered primordial and either stable or weakly radioactive. The remaining 14 naturally occurring elements possess half-lives too short for them to have been present at the beginning of the Solar System, and are therefore considered transient elements. Of these 14 transient elements, 7 are relatively common decay products of thorium, uranium, and plutonium. The remaining 7 transient elements occur only rarely, as products of rare nuclear reaction processes involving uranium or other heavy elements. Elements with atomic numbers 1 through 40 are all stable, while those with atomic numbers 41 through 82 are metastable. The half-lives of these metastable theoretical radionuclides are so long that their radioactive decay has yet to be detected by experiment. Elements with atomic numbers 83 through 98 are unstable to the point that their radioactive decay can be detected. Some of these elements, notably thorium and uranium, have one or more isotopes with half-lives long enough to survive as remnants of the explosive stellar nucleosynthesis that produced the heavy elements before the formation of our solar system. For example, at over 1.9 1019 years, over a billion times longer than the current estimated age of the universe, bismuth 209 has the longest known alpha decay half-life of any naturally occurring element. The very heaviest elements undergo radioactive decay with short half-lives and do not occur in nature. The periodic table. The properties of the chemical elements are often summarized using the periodic table, which powerfully and elegantly organizes the elements by increasing atomic number into rows in which the columns share recurring physical and chemical properties. The current standard table contains 118 confirmed elements as of April 10, 2010. Although earlier precursors to this presentation exist, its invention is generally credited to the Russian chemist Dmitry Mendeleev in 1869, who intended the table to illustrate recurring trends in the properties of the elements. The layout of the table has been refined and extended over time as new elements have been discovered and new theoretical models have been developed to explain chemical behavior. Use of the periodic table is now ubiquitous within the academic discipline of chemistry, providing an extremely useful framework to classify, systematize and compare all the many different forms of chemical behavior. The table has also found wide application in physics, geology, biology, materials science, engineering, agriculture, medicine, nutrition, environmental health, and astronomy. Its principles are especially important in chemical engineering. Nomenclature and symbols. The various chemical elements are formally identified by their unique atomic numbers, by their accepted names, and by their symbols. Atomic numbers. The known elements have atomic numbers from 1 through 118, conventionally presented as Arabic numerals. Since the elements can be uniquely sequenced by atomic number, conventionally from lowest to highest, sets of elements are sometimes specified by such notation as through, beyond, or from. Through, as in through iron, beyond uranium, or from lanthanum through lutetium. The terms light and heavy are sometimes also used informally to indicate relative atomic numbers, as in lighter than carbon, or heavier than lead, although technically the weight or mass of atoms of an element do not always increase monotonically with their atomic numbers. Element names. The naming of various substances now known as elements precedes the atomic theory of matter, as names were given locally by various cultures to various minerals, metals, compounds, alloys, mixtures, and other materials, although at the time it was not known which chemicals were elements and which compounds. As they were identified as elements, the existing names for anciently known elements were kept in most countries. National differences emerged over the names of elements either for convenience, linguistic niceties, or nationalism. For a few illustrative examples, German speakers use Wasserstoff for hydrogen, Sauerstoff for oxygen, and Stickstoff for nitrogen, while English and some Romance languages use sodium for natrium, and potassium for kalium, and the French, Italians, Greeks, Portuguese and Poles prefer azote for nitrogen. For purposes of international communication and trade, the official names of the chemical elements both ancient and more recently recognized are decided by the International Union of Pure and Applied Chemistry, which is decided on a sort of international English language, drawing on traditional English names even when an element's chemical symbol is based on a Latin or other traditional word, for example adopting gold rather than aurum as the name for the 79th element. IUPAC prefers the British spellings aluminium and cesium over the US spellings aluminum and cesium, and the US sulfur over the British sulfur. However, elements that are practical to sell in bulk in many countries often still have locally used national names, and countries whose national language does not use the Latin alphabet are likely to use the IUPAC element names. According to IUPAC, chemical elements are not proper nouns in English. Consequently, the full name of an element is not routinely capitalized in English, even if derived from a proper noun, as in Californium and Einsteinium. Isotope names of chemical elements are also uncapitalized if written out, for example, carbon-12 or uranium-235. Chemical element symbols are always capitalized. In the second half of the 20th century, physics laboratories became able to produce nuclei of chemical elements with half-lives too short for an appreciable amount of them to exist at any time. These are also named by IUPAC, which generally adopts the name chosen by the discoverer. This practice can lead to the controversial question of which research group actually discovered an element, a question that has delayed naming of elements with atomic number of 104 and higher for a considerable time. Precursors of such controversies involved the nationalistic namings of elements in the late 19th century. For example, lutetium was named in reference to Paris, France. The Germans were reluctant to relinquish naming rights to the French, often calling it cashium. Similarly, the British discoverer of niobium originally named it columbium, in reference to the New World. It was used extensively as such by American publications prior to international standardization. Chemical symbols. Specific chemical elements. Before chemistry became a science, alchemists had designed arcane symbols for both metals and common compounds. These were however used as abbreviations in diagrams or procedures. There was no concept of atoms combining to form molecules. With his advances in the atomic theory of matter, John Dalton devised his own simpler symbols, based on circles, to depict molecules. The current system of chemical notation was invented by Berzelius. In this typographical system, chemical symbols are not mere abbreviations though each consists of letters of the Latin alphabet. They are intended as universal symbols for people of all languages and alphabets. The first of these symbols were intended to be fully universal. Since Latin was the common language of science at that time, they were abbreviations based on the Latin names of metals. Cu comes from cuprum, Fe comes from ferrum, Ag from argentum. The symbols were not followed by a period as with abbreviations. Later chemical elements were also assigned unique chemical symbols, based on the name of the element, but not necessarily in English. For example, sodium has the chemical symbol now after the Latin natrium. The same applies to W for tungsten, Fe for iron, Hg for mercury, Sn for tin, K for potassium, or for gold, Ag for silver, Pb for lead, Cu for copper, and Sp for antimony. Chemical symbols are understood internationally when element names might require translation. There are sometimes differences. For example, the Germans have used J instead of I for iodine, so the character would not be confused with a Roman numeral. The first letter of a chemical symbol is always capitalized, as in the preceding examples, and the subsequent letters, if any, are always lowercase. Thus, the symbols for californium or einsteinium are CF and Is. General chemical symbols. There are also symbols in chemical equations for groups of chemical elements, for example in comparative formulas. These are often a single capital letter, and the letters are reserved and not used for names of specific elements. For example, an X indicates a variable group in a class of compounds, while R is a radical, meaning a compound structure such as a hydrocarbon chain. The letter Q is reserved for heat in a chemical reaction. Y is also often used as a general chemical symbol, although it is also the symbol of yttrium. Z is also frequently used as a general variable group. E is used in organic chemistry to denote an electron withdrawing group. L is used to represent a general ligand in inorganic and organometallic chemistry. M is also often used in place of a general metal. At least two additional, two-letter generic chemical symbols are also in informal usage, Ln for any lanthanide element and N for any actinide element. Rg was formerly used for any rare gas element, but the group of rare gases has now been renamed noble gases and the symbol Rg has now been assigned to the element runtgenium. Isotope symbols. Isotopes are distinguished by the atomic mass number for a particular isotope of an element, with this number combined with the pertinent element symbol. IUPAC prefers that isotope symbols be written in superscript notation when practical, for example 12C and 235U. However, other notations, such as carbon-12 and uranium-235, or C12 and U-235, are also used. As a special case, the three naturally occurring isotopes of the element hydrogen are often specified as H for 1 hour, D for 2 hours, and T for 3 hours. This convention is easier to use in chemical equations, replacing the need to write out the mass number for each atom. For example, the formula for heavy water may be written D20 instead of 2 hours 20. Origin of the elements. Only about 4% of the total mass of the universe is made of atoms or ions, and thus represented by chemical elements. This fraction is about 15% of the total matter, with the remainder of the matter being dark matter. The nature of dark matter is unknown, but it is not composed of atoms of chemical elements because it contains no protons, neutrons, or electrons. The universe's 98 naturally occurring chemical elements are thought to have been produced by at least 4 cosmic processes. Most of the hydrogen and helium in the universe was produced primordially in the first few minutes of the Big Bang. 3 recurrently occurring later processes are thought to have produced the remaining elements. Stellar nucleosynthesis, an ongoing process, produces all elements from carbon through iron in atomic number, but little lithium, beryllium, or boron. Elements heavier in atomic number than iron, as heavy as uranium and plutonium, are produced by explosive nucleosynthesis in supernovas and other cataclysmic cosmic events. Cosmic ray spallation of carbon, nitrogen, and oxygen is important to the production of lithium, beryllium and boron. During the early phases of the Big Bang, nucleosynthesis of hydrogen nuclei resulted in the production of hydrogen-1 and helium-4, as well as a smaller amount of deuterium and very minuscule amounts of lithium and beryllium. Even smaller amounts of boron may have been produced in the Big Bang, since it has been observed in some very old stars, while carbon has not. It is generally agreed that no heavier elements than boron were produced in the Big Bang. As a result, the primordial abundance of atoms consisted of roughly 75% 1 hour, 25% for He, and 0.01% deuterium, with only tiny traces of lithium, beryllium, and perhaps boron. Subsequent enrichment of galactic halos occurred due to stellar nucleosynthesis and supernova nucleosyntheses. However, the element abundance in intergalactic space can still closely resemble primordial conditions, unless it has been enriched by some means. On Earth, trace amounts of various elements continue to be produced from other elements as products of natural transmutation processes. These include some produced by cosmic rays or other nuclear reactions, and others produced as decay products of long-lived primordial nuclides. For example, trace amounts of carbon-14 are continually produced in the atmosphere by cosmic rays impacting nitrogen atoms, and argon-40 is continually produced by the decay of primordially occurring but unstable potassium-40. Also, 3 primordially occurring but radioactive actinides, thorium, uranium, and plutonium, decay through a series of recurrently produced but unstable radioactive elements such as radium and radon, which are transiently present in any sample of these metals or their ores or compounds. 7 other radioactive elements, technetium, promethium, neptunium, americium, curium, berkelium, and californium, occur only incidentally in natural materials, produced as individual atoms by natural fission of the nuclei of various heavy elements or in other rare nuclear processes. Human technology has produced various additional elements beyond these first 98, with those through atomic number 118 now known. Abundance. The following graph shows the abundance of elements in our solar system. The table shows the 12 most common elements in our galaxy, as measured in parts per million, by mass. Nearby galaxies that have evolved along similar lines have a corresponding enrichment of elements heavier than hydrogen and helium. The more distant galaxies are being viewed as they appeared in the past, so their abundances of elements appear closer to the primordial mixture. As physical laws and processes appear common throughout the visible universe, however, scientists expect that these galaxies evolved elements in similar abundance. The abundance of elements in the solar system is in keeping with their origin from nucleosynthesis in the Big Bang and a number of progenitor supernova stars. Very abundant hydrogen and helium are products of the Big Bang, but the next 3 elements are rare since they had little time to form in the Big Bang and are not made in stars. Beginning with carbon, elements are produced in stars by buildup from alpha particles, resulting in an alternatingly larger abundance of elements with even atomic numbers. In general, such elements up to iron are made in large stars in the process of becoming supernovas. Iron 56 is particularly common, since it is the most stable element that can easily be made from alpha particles. Elements heavier than iron are made in energy-absorbing processes in large stars, and their abundance in the universe generally decreases with their atomic number. The abundance of the chemical elements on Earth varies from air to crust to ocean, and in various types of life. The abundance of elements in Earth's crust differs from that in the universe mainly in selective loss of the very lightest elements and also volatile neon, carbon, nitrogen and sulfur, as a result of solar heating in the early formation of the solar system. Aluminum is also far more common in the Earth and Earth's crust than in the universe and solar system, but the composition of Earth's mantle more closely mirrors that of the universe, save for the noted loss of volatile elements. The composition of the human body, by contrast, more closely follows the composition of seawater save that the human body has additional stores of carbon and nitrogen necessary to form the proteins and nucleic acids characteristic of living organisms. Certain kinds of organisms require particular additional elements, for example the magnesium in chlorophyll in green plants, the calcium in mollusk shells, or the iron in the hemoglobin in vertebrate animals' red blood cells. History. Evolving definitions. The concept of an element as an undivisible substance has developed through 3 major historical phases: classical definitions, chemical definitions, and atomic definitions. Classical definitions. Ancient philosophy posited a set of classical elements to explain observed patterns in nature. These elements originally referred to earth, water, air and fire rather than the chemical elements of modern science. The term elements was first used by the Greek philosopher Plato in about 360 BCE in his dialogue Timaeus, which includes a discussion of the composition of inorganic and organic bodies and as a speculative treatise on chemistry. Plato believed the elements introduced a century earlier by Empedocles were composed of small polyhedral forms, tetrahedron, octahedron, icosahedron, and cube. Aristotle, c. 350 BCE, also used the term stoichua and added a fifth element called ether, which formed the heavens. Aristotle defined an element as element one of those bodies into which other bodies can decompose, and that itself is not capable of being divided into other chemical definitions. In 1661, Robert Boyle proposed his theory of corpuscularism, which favored the analysis of matter as constituted by irreducible units of matter and, choosing to side with neither Aristotle's view of the four elements nor Paracelsus' view of three fundamental elements, left open the question of the number of elements. The first modern list of chemical elements was given in Antoine Lavoisier's 1789 Elements of Chemistry, which contained 33 elements, including light and caloric. By 1818, Jar paragraph N.S. Jacob Berzelius had determined atomic weights for 45 of the 49 then accepted elements. Dmitry Mendeleev had 66 elements in his periodic table of 1869. From Boyle until the early 20th century, an element was defined as a pure substance that could not be decomposed into any simpler substance. Put another way, a chemical element cannot be transformed into other chemical elements by chemical processes. Elements during this time were generally distinguished by their atomic weights, a property measurable with fair accuracy by available analytical techniques. Atomic definitions. The 1913 discovery by English physicist Henry Moseley that the nuclear charge is the physical basis for an atom's atomic number, further refined when the nature of protons and neutrons became appreciated, eventually led to the current definition of an element based on atomic number. The use of atomic numbers, rather than atomic weights, to distinguish elements has greater predictive value, and also resolves some ambiguities in the chemistry-based view due to varying properties of isotopes and allotropes within the same element. Currently, IUPAC defines an element to exist if it has isotopes with a lifetime longer than the 10 or 14 seconds it takes the nucleus to form an electronic cloud. By 1914, 72 elements were known, all naturally occurring. The remaining naturally occurring elements were discovered or isolated in subsequent decades, and various additional elements have also been produced synthetically, with much of that work pioneered by Glenn T. Seaborg. In 1955, element 101 was discovered and named Mendelevium in honor of D. I. Mendeleev, the first to arrange the elements in a periodic manner. Most recently, the synthesis of element 118 was reported in October 2006, and the synthesis of element 117 was reported in April 2010. Discovery and recognition of various elements. 10 materials familiar to various prehistoric cultures are now known to be chemical elements: carbon, copper, gold, iron, lead, mercury, silver, sulfur, tin, and zinc. 3 additional materials now accepted as elements, arsenic, antimony, and bismuth, were recognized as distinct substances prior to 1500 AD. Phosphorus, cobalt, and platinum were isolated before 1750. Most of the remaining naturally occurring chemical elements were identified and characterized by 1900, including such now familiar industrial materials as aluminium, silicon, nickel, chromium, magnesium, and tungsten, reactive metals such as lithium, sodium, potassium, and calcium, the halogens fluorine, chlorine, bromine, and iodine, gases such as hydrogen, oxygen, nitrogen, helium, argon, and neon, most of the rare earth elements, including cerium, lanthanum, gadolinium, and neodymium. The more common radioactive elements, including uranium, thorium, radium, and radon, elements isolated or produced since 1900 include the 3 remaining undiscovered regularly occurring stable natural elements, hafnium, lutetium, and rhenium, plutonium, which was first produced synthetically in 1940 by Glenn T. Seaborg, but is now also known from a few long-persisting natural occurrences, the 3 incidentally occurring natural elements, which were all first produced synthetically but later discovered in trace amounts in certain geological samples, 3 scarce decay products of uranium or thorium and various synthetic transuranic elements, beginning with americium, curium, berkelium, and californium, recently discovered elements, The first transuranium element discovered was neptunium in 1940. Since 1999, claims for the discovery of new elements have been considered by the IUPAC-IUPAP Joint Working Party. As of May 2012, only the elements up to 112, Copernicium, as well as element 114 flerovium and element 116 livermorium have been confirmed as discovered by IUPAC, while claims have been made for synthesis of elements 113, 115, 117 and 118. The discovery of element 112 was acknowledged in 2009, and the name Copernicium and the atomic symbol Cn were suggested for it. The name and symbol were officially endorsed by IUPAC on February 19, 2010. The heaviest element that is believed to have been synthesized to date is element 118, Untitled, on October 9, 2006, by the Flerov Laboratory of Nuclear Reactions in Dubna, Russia. Element 117 was the latest element claimed to be discovered, in 2009. IUPAC officially recognized flerovium and livermorium, elements 114 and 116, in June 2011 and approved their names in May 2012. List of the 118 known chemical elements. The following sortable table includes the 118 known chemical elements, with the names linking to the Wikipedia articles on each. Atomic number, name, and symbol all serve independently as unique identifiers. Names are those accepted by IUPAC. Provisional names for recently produced elements not yet formally named are in parentheses. Group, period, and block refer to an element's position in the periodic table. Group numbers here show the currently accepted numbering. For older alternate numberings, see group. State of matter applies at standard temperature and pressure conditions. Occurrence distinguishes naturally occurring elements, categorized as either primordial or transient, and additional synthetic elements that have been produced technologically, but are not known to occur naturally. Description summarizes an element's properties using the broad categories commonly presented in periodic tables: actinide, alkali metal, alkaline earth metal, halogen, lanthanide, metal, metalloid, noble gas, non-metal, and transition metal. See also. References. Further reading, Ball, P. The Elements, A Very Short Introduction. Oxford University Press. ISBN A0-19-284099-1 Emsley, J. Nature's Building Blocks, An AZ Guide to the Elements. Oxford University Press. ISBN A0-19-850340-7 Gray, T. The Elements, A Visual Exploration of Every Known Atom in the Universe. Black Dog and Leventhal Publishers Incorporated. ISBN A1-57912-814-9 Seri, E.R. The Periodic Table, Its Story and Its Significance. Oxford University Press. Strathern, P. Mendeleïev's Dream, The Quest for the Elements. Hamish Hamilton Limited. ISBN A0-241-14065 Keane, Sam. The Disappearing Spoon, and Other True Tales of Madness, Love, and the History of the World from the Periodic Table of the Elements. Back Bay Books. External links, videos for each element by the University of Nottingham.